All right, let's talk about exponential functions and consider what their graphs look like. Now, you and I so far have been looking at functions like this. Here are a couple of our basic functions. F of x equals x squared. Remember this guy? The quadratic function. Oh yeah, Mr. Parabola. How about f of x equal x cubed? These guys are all on your basic function worksheets that I provided for you. This guy looks like that, remember? How about f of x equals x fourth? You probably remember it's just a thinner version of the parabola. And how about consider this one? F of x is x to the 1/2. You know now that since you've talked about rational exponents, fractional exponents, that something to the 1/2 simply means the square root of that thing. Remember what the square root of x looks like? Looks like this. Hey, notice something that is in common with each of these functions. X is the base. The exponent's changing. X is the base in these particular functions. Well, in the case of exponential functions, x is not the base, but it's actually the exponent. Watch this. Here's an example of an exponential function. So when you pick an x, you're picking the exponent. One thing you should note about the typical, of course you know that it could be written as y equals a to the x. One thing you should note about the exponential function is that your base has to be positive. Otherwise, you're going to find yourself in positions of taking the 1/2 power, which of course is the square root of a negative number. So this can't be negative. Now the question is, what happens when I pick a particular base? Like what, for instance, does f of x equal 3 to the x? What does that look like? Well, thanks for asking, because that just happens to be the first problem on your Hawks assignment. It's going to have, as you know, 4 graphs, and it's going to say which of these 4 graphs is the correct graph for m of x equals 3 to the x. There's a variety of ways to do this. The way I suggest you do it is take some very specific x's and find out what the y is going to be. Remember, m of x equals is the same as y equals 3 to the x. So if I were you, I would strategically pick some x's so that you can find out what y is. One thing you know for sure is that 3 to the 0 power is what? Remember? That's 1. Anything to the 0 power, any real number to the 0 power, 1. And you know that 3 to the first power is another name for 3. And you know 3 to the second power is 9. Those are very simple, common powers of 3. So if I were you, I would pick 0, 1, and 2 for my x's. Let x be 0, let x be 1, let x be 2. Well, if x is 0, then y is 3 to the 0 power, which is 1. If x is 1, y is 3 to the first power, which is 3. If x is 2, y is 3 to the second power, which is 9. So let's look and see what this guy looks like. First of all, at 0, I get 1. At 1, I get 1, 2, 3. At 2, I get 9. 3, 4, 5, 6, 7. So check this guy out. I say, I wonder what's going to happen on this side of the y-axis. Let's try -1 and -2. But by the way, these points are going to be enough to figure out which of the 4 graphs is your graph. Your graph is the one that has these 3 strategic points on it. But let's see what happens with x when x is -1. That means y is 3 to the -1. Oh, wait a minute, but a negative exponent is a reciprocal concept, right? That means I can move it to the other part of the fraction and make this 1/3. So if I pick x as -1, 3 to the -1 is the same as 1 over 3 to the +1, 1/3. So if x is -1, I get 1/3. How about -2? If x is -2, 3 to the -2, oh yeah, that's the same as 1 over 3 to the +2, which is 1/9. So if x is -2, I get 1/9. You can see these are getting smaller and smaller and smaller. Getting closer and closer to the x-axis, but we'll never touch it. It's what you call asymptotic too, right? All right, there's the look of the graph. Y equals 3 to the x. And that is going to be basically the look of the graph if my a, my base here, is greater than 1. It's going to go up like this. If I pick something between 0 and 1, remember it's got to be positive. If I pick something like 1/2, 1/4, 1/3, it's going to go in the opposite direction, like this. But you can figure by a few strategic points as to what it's actually doing. So which is the graph? The one that looks just like that. Right, a similar question. Which is the correct graph for q of x equal, oh my goodness, 2 to the x minus 4? Wow. Well, we're still going to need some points. We're still going to need some x's and y's. So let's find some x's and y's. Now remember, things I'm familiar with are these concepts. 2 to the 0 power, that's 1, right? Anything to the 0 power. 2 to the first power, that just means 2. And 2 squared is 4. If you want to go up, 2 to the third is 8. These are things I'm familiar with. But what x would I have to pick to make this exponent 0? That's right, 4 minus 4. If I pick x as 4, then 2 to the 4 minus 4 is 2 to the 0. And 2 to the 0 is 1. So I get the point 4, 1. When I pick x as 4, I get 1. All right, what would I have to pick for my x to make the exponent of 1? What minus 4 is 1? Yeah, 5. If I pick x as 5, 5 minus 4 is 2 to the 1th power, and that's just 2. So if I pick x for 5, I get 2. What would I have to pick for x to get an exponent of 2? What minus 4 is 2? 6. I get 2 to the 6 minus 4, which is 2. If I choose x is 6, I get 4. 6, 1, 2, 3, 4. And you can guess if I pick x is 7, I'm going to get 8. So here's the look of the graph now. And when you pick your graph, you're going to be picking something that looks like this. But it's going to have these strategic points: 4, 1, 5, 2, 6, 4. Pick the graph that has those points. So that's, in my mind, the best way to figure out what this graph looks like is to pick an x so that it gives you an exponent that you can easily evaluate. All right. The other type of problem you're going to see in this section is solving exponential equations. Now, I don't know about you, but if you don't have an expertise, that looks pretty sophisticated. In fact, it looks, in my mind, impossible. So here's what we're going to do. We're going to follow some steps. We're going to first of all isolate the exponential expression. Just like if it was a absolute value or other squared value, isolate the exponential term. Well, that's easy. I just add 125 to both sides, right? And I get 25 to the x is 125. Now, most of you are probably looking at that going, well, that doesn't get me any closer to where I need to be. All right, here's your second strategy. And this is the strategy that you're going to apply to each of these problems. Express both sides with the same base. In other words, make them both something to a power. Well, that doesn't take a lot to look at 25 and know that that's 5 squared, right? And you have a little chart that says 125 is 5 to the third. So in the place of 25, I'm going to put 5 squared. But remember, it's 25 to the x, right? So in the place of 25, all I did is put 5 squared. In the place of 125, same base, I'm going to put 5 to the third. Now here's what we're going to do. We're going to express both sides as 5 to some power. Look what you have here. You have a power to a power. What do you do when you have a power to a power? You multiply your exponents. So I get 5 to the 2x equals 5 to the third. Now, ladies and gentlemen, here is the principle that you're going to use in every one of these problems. As soon as I have the same base, and I can put this as step 3, same base implies exponents are equal. Hey, if I have 5 to something equal 5 to something, then the two somethings must be the same. So if I have the same base implies the exponents are equal. So my next step is to conclude that 2x equals 3. Hey, look how close we are to solving this equation for x. All I have to do is divide both sides by 2, and I find that x is 3 over 2. Now, it certainly isn't obvious, is it, that 3 over 2 is going to be the answer to this? This is something that you have to work out with the steps. Get your exponential term by itself, express each side, and it's got to be both sides, as the same thing to a power with the same base. Once you have them expressed with the same base, then their exponents must be equal. That will allow you to solve for x. Right? Let's check out this guy. Solve the following exponential equation. I don't know about you, but that looks virtually impossible unless I follow my steps. Isolate the exponential term. It's isolated. There it is. Express both sides with the same base. They don't have the same base right now, but you probably are determining that 1/4 may be expressed as 1/2 times 1/2, right? So in the place of 1/4, I'm going to say that's 1/2 squared. 1/2 times 1/2 is 1/4. So in the place of 1/4, I'm going to put 1/2 squared. So I got 1/2 to this strange exponent equals 1/2 squared. There's my 1/4 right there, but that's also squared. See, there's my 1/4 right there. 1/4 is the same as 1/2 squared. 1/4 squared is what I got here. Hey, I'm one step away, right? Power to a power, I multiply. So 1/2 to the 3x plus 4 equals 1/2 to the 4. Hey, I got the same base. That means my exponents must be equal. So 3x plus 4 must be equal to 4. Minus 4 minus 4. 3x is 0. Divide both sides by 3. X equals 0. Ain't not too bad at all, huh? Alright, but these steps are going to be key to solving these equations. Solve the following exponential equation. Alright, my exponential term is isolated, it's by itself. My next idea is to think, what could be the common base? Can I express one of these as the other to a power? Yeah, 8 is the same as 2 to the 3rd, isn't it? That's on your chart. 8 is the same as 2 to the 3rd. So in the place of 8, I'm going to put 2 to the 3rd. But it's 8 to the negative x. Don't forget that other exponent. Now I'm going to go ahead and write 2 as 2 to the 1st. So I can see that they have the same base. They both have exponents. Look here. Power to a power. What do you do with these exponents? That's right, you multiply. Negative x times 3, negative 3x. Looky there, I got the same base. That means my two exponents are equal. So negative 3x equals 1. I need to find out what x is, so I'm going to divide by negative 3. And I get x is negative 1/3. Hey, not too bad, huh? So the idea is to express both sides as the same base to a power. And then I can equate my powers. All right, this was going to be easy because we're going to very easily think what I can express this as 10 to some power, right? And you probably know this. Count the number of zeros. That's 10 to that power. So if I have in 10,000, 1, 2, 3, 4 zeros, that's the same as 10 to the 4th. So 10,000 is the same as 10 to the 4th. So in the place of 10,000, I'm going to put 10 to the 4th. Now remember, it's 10 to the 4th to the negative x power. It's equal to 10 to the x minus 10. Power to a power, multiply your exponents. 4 times negative x, negative 4x. Right, notice, same base. That means my two exponents must be equivalent. So I get negative 4x is x minus 10. I want to solve for x, so I need to get my x's together. I'm going to subtract x from both sides. It's negative 5x equals negative 10. Divide negative 5, and I got it. It came out nice and neat, didn't it? All right. This one's got a little bit more challenge to it, mainly because I got a fraction here. But it's still basically the same concept. Isolate your exponential term, done. Now I need to express both sides as the same base to a power. Can you guess what that base is going to be? You probably see 49. That's 49 is the same as 7 squared. So in the place of 49, I'm going to put 7 squared. So is this the same base to the, am I ready to go and equate my, no. This is 7, this is 1/7. So these are two different bases. This is 7 to that power, this is 1/7 to that power. So not until I make my strategic move, because any factor to a power may be moved to the other part of the fraction if I change the sign of my exponent. So 1/7 to the 2 is 7 to the negative 2. Usually we move the term that's got the negative exponent to make things positive, make exponents positive. But in this case, we moved the positive exponent and made it negative because we need to have the same base. And we do now. Look here. Got the same base. That means that my exponents are equivalent. 3x minus 5 is the same as negative 2. This is a pretty good problem. See, I'm going to add 5 to both sides. 3x is 3. Divide by 3, x is 1. All right. So that's the last of those examples. The last one is similar to the first two, which is the correct graph 4. And notice I got a fraction here, so it's going to make it a little bit challenging, but not too much challenging, because I know a couple of specific things. Number one, 1/4 to the 0 power is going to be 1, because any real number to the 0 power is 1. And I also know that 1/4 to the first power is 1/4. Anything to the first power is itself. So with these two concepts, I'll bet you I can come up with a couple of points, x and y, that will show me which of these 4 graphs they give me is the correct graph. So I want 1/4 to the 0 power. Here's the question. What does x have to be to make this whole exponent 0? 2 minus what is 0? That's right, 2. 2 minus 2 is 0. 1/4 to the 0 power is 1. Now I want to make the exponent 1. What does x have to be to make the exponent here 1? 2 minus what is 1? Well, 1. 2 minus 1 is 1. 1/4 to the first power is 1/4. So here's what I would do. I would plot these 2 points. X is 2, y is 1. X is 1, y is 1/4. Is that enough to let you know what it's going to look like? Let's do one more just for grins here. Let's do 3. Yeah, tell you what, let's do 0. 2 minus 0 is 2. 1/4 to the second power means 1/4 squared. That's 1/16. So I get 1/16. If x is 0, I get 1/16. You see what it's doing? It's getting asymptotic here, getting closer and closer, and of course it's going to go higher and higher here. In fact, if I did 0, 1, 2, 3, 2 minus 3 is -1. 1/4 to the -1 is the same as the reciprocal to the +1, and that's just 4. So for 3, I'm going to get 4. And the next one's going to be 16. It's going to take off here, so it's going to... But these two are the ones that were very easy to get. And believe me, only one of the graphs will have these 2 points. 1/4 and 2, 1. All right, those are the only 2 types of problems that you will see in this section. We're just about to the end of it. One more section to go before the due date. Logarithmic functions, which, by the way, are the inverses of your exponential functions. We'll get to that next time.